State, who will talk about ultrafast physics with mid-infrared drivers beyond lambda scaling.
So my name is Cosmin Blaga, and I'm here to represent the Agustini tomorrow group at OSU. But in actuality, most of the data that I'm going to show was taken in collaboration with Gino Ling's group, so I feel quite connected to the home team here. And I will also show you some new results that we have with Matthias Kling's group, that we haven't published yet, but they're really excited and I'm really happy to share them with you. So the idea of the talk is very simple. Most of the stuff that we learned in strong field physics over the years was done with visible and near infrared pulses, right? And everything we learned about these fundamental blocks was that mid-infrared drivers would be very helpful for a lot of these processes, and the reason is very simple. The scattering mechanism is more energetic along the wavelengths, right? So that's the whole thing. So we've been actively pursuing mid-infrared pulses for a long time in our lab, and indeed, the predictions of these fundamental processes, the predictions that longer wavelengths will be helpful, turn out to be true. But we also discovered essentially new things at these mid-infrared wavelengths, and I think it's pretty safe to assume that as we keep pursuing longer and longer wavelengths, newer things and more interesting stuff will happen. So new physics will be uncovered. So the outline of my talk is pretty simple. In the beginning, I'm just going to show you how this wavelength scaling works. I'm not going to spend too much time on it. I'm just going to give you several experimental confirmations that we uncovered. And then I'm going to go straight to present you these new phenomena that are visible with mid-infrared wavelengths, but they were hidden or not possible with shorter wavelengths. And the first two are relatively related. I'm going to talk about low energy structures in photoelectron spectra, and this is something that we've studied quite a bit. And also I'm going to touch on holography with photoelectrons, and this was brought forward by Mark Racken's collaboration in 2011. And I'm not going to spend too much time on either one of these topics. Basically, the reason is my interest is in molecular imaging. And we heard a lot about dynamics, watching, for example, chemical reactions in the last few days. And you can think of a chemical reaction very simply. In the most simple way is you have the electron. Electron dynamics starts first in its attosecond time scale, and then the nuclei kind of follow after that on some much longer time, like femtosecond scale. So ideally, you want to watch this dynamic with 2 attosecond pulses, but this is not easy, especially on a tabletop in the lab, because the harmonic sources, the attosecond pulses are relatively weak, so it's very difficult to see that. So the next best thing would be to develop a tool that has actually femtosecond resolution to watch the nuclei. So you do something, you start something with the harmonics, and then sometimes later you investigate the nuclei with femtosecond resolution. So the imaging method, the requirements that you would like it to have, obviously, is temporal and spatial resolution. So you want femtosecond temporal resolution and sub-angstrom spatial resolution. You want it to be as general as possible. If you develop any method, right? Because people have different laser fields in the lab and so on, so you want it to be general and not depend on laser parameters or the target system. You want it to be as reliable as possible, obviously, and you want it to be as simple as possible. So whatever you see, ideally you want to have as few modeling as you can. You want to keep it as simple as possible, right? So these are the requirements. So now, as I said, I'm going to focus on these two. On the first one, molecular imaging, laser-induced electron diffraction. This is basically a cross-section in the angular domain, and we have. I'm going to show you some published results that we had, but I'm also going to show you some new things. And then I'm going to conclude with this new imaging way using broadband electron pulses. As far as I know, this is entirely new. The paper is about to be submitted, but I think it's something new for you. So I'm very happy to share it. All right. So the introduction, as I said, is pretty simple. Basically, the bottom line here is the longer wavelengths lead to higher collisions. It's very simple. The rescattering mechanism it gives you maximum electron energy that is proportional with UP. UP is the Pontryagin potential, is the average kinetic energy of free electron in laser field. This is the quiver energy, and it scales with lambda squared times the intensity of the laser. Now, the intensity usually is limited by the depletion of the ground state or the saturation intensity. So to really generate more higher and higher collisions, the best tool is to use to increase the wavelength. That's the obvious way to approach the problem. All right. So before I go into it, I'm going to give you a quick view of what the sources, data sources at OSU and the detection chambers. So we have an 800 nanometer CEP stabilized system. This is a femtolane system, it's commercial. Then we have a home built 1 kilohertz, also 800 nanometer, 50 femtosecond, 7 millijoule titanium sapphire system. And it's currently pumping a commercial OPA. It's based on BBO, so it's tunable from 1.2 to 2.5 microns, with perhaps a very small gap near degeneracy around 1.6. And the third system is it's another TISAF system, slightly weaker than this one, so 80 femtosecond and only 3.5 millijoules. And it's currently pumping the newest addition to the family. This is a home-built mini-infrared tunable laser. Goes between 2.5 to 5 microns. It puts about 140 microjoules at mid-range, around at 3.5 microns, and makes 80 femtosecond pulses. In terms of detection chambers, we have a nanosecond beam line. We have an XUV spectrometer. We just finished the construction of a VMI that can see electrons up to a kilo electron volts for recording angle distributions really quickly. And finally, we have time-of-flight machines that have time bins greater than 50 picoseconds or longer. And the length of the time-of-flight spectrometers are, one has about a quarter of a meter and the other one is about half a meter. Okay, so the experimental observations of this, that lambda scaling actually works. So I'm going to start with elastic scattering. As you increase the driving wavelength from 800 nanometers to 3.6, and when we look at the photoelectron spectrum along the laser polarization, what you see an increase in the entire spectrum. So at 800, it's really it only produces relatively low energy electrons. If you go to 3.6, you can see up to a kilo electron volt. This is a classical photoelectron spectrum, if you want to think like that. From 0 to up to about 2 UP, you get this very, very sharp exponential decrease in yield, and then you get this scatter plateau that was discovered by Gerhard Pals in the mid-90s, extending all the way up to 10 UP. So you have 2 UP break, you have a 10 UP break, everything looks classical. That's fine. That's great. If I plot everything in field units, you see the same thing. You start with 800 nanometer, where gamma, the Kelch parameter is about 1.3. The distribution doesn't really look all that classical. It has this constant. There's no clear 2UP break. And the deeper you go down the regime, you go and you see this 2UP break very nicely in 3.6 microns and then extending up in. So for elastic scattering, it works. Now, what about non-sequential ionization, so inelastic scattering? So instead of elastically fast scatter, this time you produce additional electrons. This was first reported by Barry, who was a Lowell student in the mid-90s. And you see here the, I would say now famous, the helium yield spectrum. And we repeated the same type of experiment and recorded it in last year. The person that drove this experiment was actually Barry's student in the life story. So this was done at 3.6 microns in xenon, and what you see is that around 10 to 14 watt per centimeter squared, the returning energy of the electron is about 300 eV, and we produce up to xenon 6+. So the electron comes in and it does an E6E process. And Carlos mentioned here, this is a very interesting spectrum. I can talk about it quite a bit, but I don't want to focus on it at all. We do see in this experiment, we saw the 4D resonance and so on. So it's not, you're not only stripping the 6 electrons of the P, the Ds are also involved. So it's very interesting on its own right, but I'm moving forward. Then the last thing I want to show is indeed going to longer wavelengths, you get an enhanced, cutoff. So we measured the harmonic spectrum in argon around 10 to 14. So you see that when you go from 800 nanometer, which is in green, to 1.3 and 2 microns, you get a larger and larger spectrum. And on the right here, you see the cutoff that we measured in, it's about 220 eV. So that will be the harmonic spectrum, and you see it here. This is a zirconium filter. Now, this is all fine. This is all understood. So now I'm going to move to the main part of the talk, which is to describe these new things that we found. So the first one will be the low energy structure of the photoelectron spectra. So I've already showed you before this photoelectron spectrum that it's well understood, right? You have the direct electrons up to 2UP, and then you have the long scatter plateau. So you look at it, this spectrum, and everything looks fine. However, when you zoom in at the very low energy, you see that below 10 eV or so, you get this very sharp peak that when you apply SFA, here's the KFR, it is not reproduced at all. But everything else beyond that, SFA works great. And you expect SFA to work benefits the strong field approximation in this regime. So the answer was, the question that we had was like, what exactly is this thing? So when we saw this thing in 2007, we spent probably more than a year and kind of threw a kitchen sink strategy at this guy. So what you see here is a detailed investigation that was reported about this low energy structure. And in upper left panel, you see that when you go from 800 to longer and longer wavelengths, the low energy structure appears. At 800, you see nothing. You only see the ATI spectrum. But at longer and longer wavelengths produces a larger and larger structure, low energy structure. Then on the upper right panel, you see the behavior of this structure when you increase the intensity in argon. So we kept the wavelength constant, the target constant, we just put more and more intensity. And you see that indeed the structure becomes broader and broader, and it shows a clear dependence on intensity. However, because we can change intensity and the wavelength, we did it in such a way that we kept the UP constant. So we adjusted UP, the intensity and the wavelength to keep it constant. And when you plot this one for 3 different wavelengths, 1.7, 2 micron, and 2.3 with the corresponding intensities, we found that actually the low energy structure doesn't depend at all on UP. So that kind of gives you an idea that it's a field-driven process, right? Then finally, what I have here is a dependence on the polarization of the light. we did linear polarization, which is everything else was reported here. You see the low energy structure. But when you switch to circular polarization, there's nothing, right? So this is, anybody in the field that have done, harmonization knows that this is a clear indication of some sort of rescattering going on, right? So you need linear polarization to drive some rescattering. And the last slide that I want to show, also indicative that the rescattering is was probably important at the time. We recorded the angular distribution by rotating the polarization in very small steps. We put a very small pinhole in front of the detector to restrict the angle and to get really good angle resolution. And what we saw was that when you look at the low energy structure as a function of emission angle, it is localized to very, very small angles around the laser polarization. So basically, you go plus minus 5-6 degrees away from the laser polarization direction, and it's gone. Right? So it's very, very small parameter space. Since we reported this, there's been a lot of work done, and it turns out that our indication and our intuition was correct, and the LES originates from, it's a direct effect of the Coulomb potential on the wave packet, and it's dominated by the long tail. It is when you have very soft collisions in the presence of the Coulomb. So it's a very fundamental problem for us to understand how the wave packet behaves and what role is the Coulomb potential when doing this scattering. So it's a very interesting thing. So there's been a lot of work after that, but we're still working on it, and that's all I have right now about this. Somewhat linked to this, to the first topic, is this holography before electrons. And anybody has any questions, you can go ask Mark during the coffee break. So as I said, it was reported in 2011, and they looked at metastable xenon using a 7 micron from the FEL they have. And basically what you see is when you look at if you record an angle distribution, so this is a VMI image, along the laser polarization you have these finger structures. They're basically just like this, right? That are due, and you see here there was a more detailed theoretical investigation by the group at NRC. These are interferences due to two different wave packets that are born a slightly different time within the same quarter cycle, and they call it A and B. And you see that the B wave goes away from the core, and that's called the reference wave. And then you have another wave that it's A, and it scatters forward, and then you detect the interference between these two. So this is why it's called holography. So this is so again they're quite related to the previous one. So one can think about both of them at the same time. Now, when we looked at the angular distribution of the low energy structure, which you can see right here, we saw exactly the same thing. We saw this like fringes like pattern, and you see it here when I'm plotting it for different. I'm looking at this fixed detected momentum for as a function of detected angle, and you see these oscillations, these fringes moving across. So they're quite, and every time we look, we saw them with this kind of wavelength. So they're very robust, they're very interesting, and the hope at the time was that, as it was highlighted in the NRC paper at the end of the abstract, it says that this is a step towards imaging by means of photoelectron holography. Now, while this is actually true, we, in principle, so we went back to the lab, we did, as I said, we see them all the time. We put isobutane and N-butane, which is the two isomers. We did the data, we took data looked at the holography for isobutane and N-butane, and we basically saw no difference. So this was kind of like a bummer to us, and we thought like, well, maybe something's wrong. But then if you look here at the mechanism here, the forward scatter wave, although it comes in with relatively high, it can come in, it can revisit the ion. At the moment it revisits with relatively high energy, you can have the 3UP wave or something. It only deflects relatively small angles. So the momentum transfer of this wave, it's relatively small, and when you want to do imaging, diffraction is the momentum transfer that matters. It's not the absolute value of your incoming momentum. So it's how much it changes, not the absolute value. So when you have small angles, the momentum transfer is very small. So at the moment, I think that probably this method has a chance if you go to even longer wavelengths and you come with higher and higher collisions, so that you can increase the momentum transfer. Perhaps there's going to be some structured information that's going to be buried in this one. But at the moment, I think it could be used as it can be like a very beautiful method to look at not necessarily at the structure of your ions, but more at the returning wave packet. Maybe you can learn something about the returning wave packet. All right, so now I'm going to move to discuss molecular imaging. As I said before, the idea here is pretty simple, is that when you have an electron that is born here, it's taken apart, so the molecule is ionized, the electron goes away, spends some time in the continuum, it gets accelerated by the field, and it comes back, and the moment here, maybe like roughly like about a cycle later, it can come in and it's scattered on the molecule, therefore encoding the structured information. And then if you would to measure the momentum distribution, you should have the structured information buried in it. The question was, how exactly do you get to it? So this idea that structured information is buried into the angular distribution has been floating around for a long time in the community, since Gerhard actually even saw the plateau. And significant progress has been done over the years, and many groups have contributed to it, and I don't want to take anything away from them. And here you see several of these groups that brought contributions to it. So in the next slides, I'm going to focus on the results that we got with Qidong and we reported last year. And basically, we recorded angular distributions for molecules, and we wanted to see what kind of structured information we can get from them. Now, I'm not going to spend any time on telling you how exactly the structure is extracted. If you want to start, see how that's done, you can look in this paper and references within. This is Qidong's great work on the quantitative scattering theory. I'm just going to say that if you detect, basically the theory says that if you have the yield that you detect with momentum p at a certain angle theta, it's equal, can be factorized, it's equal with the returning wave packet multiplied with the field-free elastic scattering cross-section. And in fact, the quantitative scattering works even when you don't look at elastic scattering. You can look at inelastic scattering, and now that you work on harmonic gesture, you can replace the elastic cross-section with the Fourier combination, but I'm not going to go there. So instead of giving you every detail how the reconstruction is done, what I'm going to do next, I'm going to actually show you extracted cross-sections, and you can judge for yourself how good they are. As I said, seeing is believing, I guess. So here I have, first we tested the method for atoms. So we recorded the angular distribution in argon at 2 × 10⁻⁴. This is down to 2 microns. And from the data, by looking at the yield along this circle, which corresponds roughly to a returning electron energy of 100 eV, we extracted the cross-section that is shown here in the green squares connected by the blue lines. So it's a little bit grassy, but it's pretty clear that when you overlap it with the cross-section that was measured by conventional electron diffraction many years ago, 1976, by Bond and Root, what we found is that we can accurately get the positions of the diffraction minima around like 60 and the one around 120. We get the maxima accurate around 90 degrees. We also get, there's a maximum at 180 degrees, but they didn't get in the experiment because they couldn't look backwards in the electron gun. So the positions of these minima and maxima, it's actually what gives you the resolution, the imaging, right? So that's actually great news. The second thing that I want to point out is that we have two orders of dynamic range. This is a log plot here, so from here to here, we extract a cross-section that is really good towards dynamic range. That's great. The third point that I want to make is that the laser extracted cross-section, which was done with femtosecond pulses, the green one, it really is identical with the field-free measurement of the bond roots, so the red squares. And this directly proves the validity and of the QRS assumption that you can factorize and only the field-free cross-sections take place. Because in the femtosecond, the cross-section that we extracted with the laser was actually imprinted when the laser was still present, right? So, and somewhat linked to it, the final point that I want to make is that in the laser case, we do not image the neutral because we have to remove an electron to actually image, so we image the ion, not the neutral. So we look at an ionic cross-section, but when you compare with the neutral cross-section, which is here displayed in red, they're absolutely identical. And this proves two things. That first, that it's a very short range interaction, right? And this is exactly what you want if you want to use this one to look at molecules. And the reason is fairly simple. If the outer shell electrons would actually matter, then you're screwed. You cannot look and hope to use this one for molecules and study chemistry. You want to be able to go and image the atom by looking at the shortest part of the potential that has no chemical signature, that doesn't have any chemical signature, right? So that's great. And finally, then this I'm going to stop with the atoms. We have to remember that the returning wave packet is actually broadband. So I showed you before the 100 dV cross section, but in fact on the same angle distribution I can extract the 100 dV, 150 dV, 200 dV, and so on. And you can see here that when you look at the maxima, the minima around like 120 dV, they do move inwards when you go to higher and higher energies. And compared with the theory and with the experimental data, this is accurate, right? So John Bragg was actually left, but I actually put this slide for him because on Monday he said that perhaps you can, even in the presence of the laser field, you can get out second resolution, right? If you want to use this in a very clever way. I don't know exactly how to do it, but the model only works if you assume that the return phase of the 100, 150, and 200 dV are different. So these are long trajectories, right? So the returning wave packet is chirped in such a way that the 200 dV electron comes first, and you get a diffraction image that you extracted and corresponds to a phase of 6.63 radians, and then 150, it's slightly longer, and then even a little longer than 100 dV. So you get the returning wave package chirp, and you get this way. In principle, you can get a series of cross-sections, a series of images, a sequence of images that are well sub-cycle. So if someone wants to use this one in the experiment, that's great. Now, the question is, how does it work for molecules? Here, I show you nitrogen. Before, how do I get any cross-section that looks good for nitrogen? And the answer is absolutely yes. Here you see we extract the cross-section of nitrogen with 100 dV. And again, you see the laser result, which is the blue curve. The green circles overlap are also the results of Root and Dubois that was extracted with the electron gun. And I barely see them because they're right on top of each other. And the red curve is the calculated cross-section by Cheatham group using the independent atom model, and that's what you see here, the IN. So how do you get structure information out of that? Well, the full differential cross-section, if you look at it as a function of scattering angle, it's expressed by, it's basically just the square of the two scattered waves from the two atoms that are in the molecule. So that's, you just have F1 plus F2 and you square it and you get the full cross-section. Now, if you actually carry out this, it's very easy, you square this thing, you get this F1 squared plus F2 squared, so it's just the squared amplitudes, which will give you just the atomic term of the cross-section. It's plotted here in black, and it means, and it dominates the cross-section. So the difference between these two curves is what gives you the structure resolution. So you're looking at a signal, when you look at the interference term, which is F1, F2 star, and its complex conjugate, it's a relatively small signal, so it's only about maybe 10% or so. However, they can calculate very well the atomic response very well. So then you take the cross-section that we showed you before in the data, you subtract the atomic term, and you plot this interference signal. And here is plotting in terms of momentum transfer, not the angle. And you see here the definition of momentum transfer. You have the incident momentum, a scatter wave, momentum transfer, which is the vectorial difference between them. So the angle maps directly into momentum transfer. And by fitting the data, we get the red curve, and that gives us the internuclear separation. And the other two curves are plus minus 5 picometers away from this thing. Okay, so how does it work for nitrogen? So we extract the internuclear distances from the diffraction image, and we see that we expect a bond length of about 1.1, and the data is great. To test the QRS and so on, we also change the wavelength, the period of the driving wavelength, and we see that 1.7 and 2.3, they all give us roughly the same result. On the x-axis here, what I'm plotting here is the time after ionization. So I'm plotting the time between this dot and that dot that the model gives me. There was no time control in the experiment other than changing the wavelength. So this is just a theoretical inferred time. Why this is important, it's because when we repeat the experiment for oxygen, instead of getting the nuclear bond around 1.2 angstrom, we actually retrieve something around 1.1 or even below 2.3, so a slightly smaller bond length. And every point here is about 3 sigmas away from what the distance that you want to see. And the reason why this happens is very simple. By the time the electron, so you produce an ion at this point here at birth via ionization, and then you come back later and image the ion. In the case of nitrogen, the internuclear separation for both the neutral and the ion is roughly the same. So when you come back and you try to image your ion, you basically measure the same distance. In the case of oxygen, you remove one electron, the oxygen bond is anti-bonding, so the internuclear separation in the ion is quite a bit smaller, so you promote a large vibrational wave packet. So by the time the electron comes back at time t, it actually does not image anymore the neutral, but it images how the molecule gets shorter. So this was direct imaging of a bond relaxation. So the question is, can we do anything for bigger molecules, right? So diatomic molecules are simple, but you're not going to impress any chemist or biologist with diatomic molecules. So we started a collaboration with Matthias Klink, and the question was, can we see anything more complicated? So so we looked at C60 with 3.6 microns of the total angle distribution, and the question is, how is the cross-section looking here? And you see that when you look at the cross-section in C60, we actually, again, reproduce very well this diffraction minima, diffraction maxima for C60 when we take 100 eV electrons out. So this is a direct measurement of the of imaging this black hole. So indeed, this laser-induced diffraction works for very large molecules, and this gives us a great hope that we can do pump probe and we can see this thing exploding and so on. We can do a lot of work with this one, hopefully in the near future. So this is really great. Now, I'm going to spend a few more minutes here. I'm going to take a couple of minutes on showing you the last result, this idea of the broadband, using the broadband pulses, which is entirely new. I've already mentioned that the returning wave packet is broadband and the rescattering, so you have access to different returning energies. So instead of changing my momentum transfer by keeping the incident momentum constant and the scatter momentum constant, just changing the angle, what I'm going to do, I'm actually going to look around 180 degrees, so I'm going to maximize the momentum transfer by fixing this angle at 180 degrees, and I'm going to use the fact that the electron wave packet is broadband, so I'm going to change the magnitude of the momentum, not the angle. And this was actually, this idea was done already for harmonic duration by ITAMP when they did the tomographic reconstruction of molecular orbitals. So what I'm going to do, like I said, I'm going to stay at 180 degrees, and I'm going to change the I'm going to look at the entire plateau. Now, the changes here are very small. You're talking about 10% changes, right? So if you want to look at the plateau, you need statistics that are better than 10%. And the plateau sits about 6 orders of magnitude below the direct electrons, right? So it's very difficult to extract it. But anyway, so we did that. We stayed a long time, and these are the results that we got. This is the 4-electron spectrum alone. This is the polarization in nitrogen and argon. We use the same idea to keep the companion atom, and oxygen and krypton. And you see that in terms of argon, these little things here, the error bars, the statistical error bar is very small. That's why everything looks very smooth. Argon, it's monotonically decreasing. Krypton the same way. Oxygen the same way. Nitrogen, it shows a very nice oscillation in the plateau. And the reason why you get that